Greetings, my name is Angel, and today me and my teammates are going to present on the topic flash drums. What is a flash drum? It's a pressure vessel used for the rapid separation of vapor liquid mixture, and it's also called a flash separator, a knockout drum, or a vapor liquid separator. Its primary purpose is to separate a high pressure, high temperature liquid stream into vapor and liquid phases by reducing its pressure. It achieves equilibrium flash vaporization. The main applications are oil and gas processing, chemical plants, refrigeration, distillation columns, etc. The goal of this design is to achieve an efficient and reliable separation at the lowest possible cost, considering both capital and operating expenses.
Okay, so I'll be discussing the dimensions and the orientation of the vessel. It isn't just about picking a random size, it is a careful calculated process that makes the whole process work. So the first up is vessel dimensions. The diameter is probably the most critical dimension in this, as the main goal here is to manage the vapor velocity. For example, imagine a wind blowing across a puddle and it'll pick up some water and carry it away, right? That's what we want to avoid inside our vessel. We size the diameter so that the vapor slows down, giving those liquid droplets a chance to fall out naturally, rather than being carried away. A bigger diameter means slower vapor, which means better separation. Now, the other important aspect is the orientation. This is where we decide if we are going to keep our vessel stand up or laid down. Most of the time, we use a vertical vessel. Why? Because gravity does half the work for us. It pulls the liquid down. However, sometimes we have to go horizontal. We'll choose if we have got a lot of liquid relative to the amount of vapor.
Hello, I'm Aruna and I'm going to be talking about the internal components of a flash drum. The internal components of a flash drum includes inlet nozzle. The inlet nozzle is designed to slow down incoming flow and encourage flashing, often incorporating features like deflector plate or tangential entry to improve dispersion. The internal components also includes a mist eliminator or the demister pad, positioned near the top to capture and remove fine liquid droplets from the vapor stream, enhancing vapor quality. Common types include mesh pads and vane style demisters. We also have the vortex breaker installed at the liquid outlet to prevent vapor entrainment into the liquid discharge line. And finally, we have the flow internals and earth baffles used to regulate flow patterns, distribute fluids evenly, and minimize surges within the vessel.
So this is Hannah. I'm here to talk about the feed conditions, temperature and pressure necessary for determining the vapor liquid equilibrium and flash point. Loading pressure causes vaporization. Composition used to find the relative volatility of components and as a result the amount of vapor and liquid formed. Operating temperature and pressure. Flash temperature, the temperature at which the mixture attains equilibrium following a reduction in pressure. Flash pressure is reduced pressure inside the drum. These to define the compositions and flow rates for vapor and liquid.
Hi, I'm Tarun and I'll be talking about the flow rates, liquid level control and separation principle of the flash drum. First, the feed flow rate helps to determine the vessel size and velocities of the vapor and liquid phases. From flash calculations, we get that the vapor and liquid flow rates, which are crucial for sizing the outlet nozzle and piping. Maintaining a stable liquid level is key to prevent vapor carry over and overflow. This control using a level transmitter and a control valve on the liquid outlet at the heart of the process in the equilibrium flash, where the feed split into vapor and liquid in thermodynamic equilibrium. This relies on KL values and is often simulated using Aspen ICs. Finally, gravity separation allows denser liquid droplets to settle and vapor bubbles to rise, provided there is enough resistance times for proper disengagement.
Hi, I'm Tahir and I'm going to talk about the critical balancing act in separator drum design: velocity, resistance, residence time, and optimization. First, vapor velocity is the gatekeeper of separation efficiency. Size the drum too small and high vapor velocity will carry over liquid droplets, contaminating the vapor stream. Size it too large and you will waste in capital. The Sodus-Brown equation gives us maximum allowable velocity. Exceed it and separation suffers. It's a trade-off. Higher velocity means a compact drum. Resistance, residence time, the silent hero. Dissolved gases need time to escape, and train bubbles need to rise. Oversizing your budget will feel it. The solution: iterate VLE checks, velocity limits, and hold up time until we strike the perfect balance. In short, right velocity, right time, right size. That's how we build separators that perform without overpaying.
So hello, this is Krishna. The last slide highlights how efficiently a flash drum design balances the performance, cost, safety and maintenance. Choosing the right dimmester pad as well as the right nozzle design is very important and reduces the entrainment losses by over 80% and improves the vapor purity by above 99.9%. Accurate instrumentation enables stable optimization operation and can save up to 10% energy. Capital cost can also be optimized using resources like Aspen, HYSYS and etc. using different methods. Safety measures like PRVs and modular internals reduce the downtime by 25%, and in this way we can conclude long-term profitability and operational reliability for a flash drum design. Thank you.